Now we just saw that the sort of principle of differentiating polynomials, things with powers x to the power of something. There's a couple of other things we just need to get clear. If I have two things added together, so if y is equal to f of x plus or minus g of x, then y or dy dx is equal to f dash x plus or minus g dash x. Now what that means is, if I have a sum or difference of different functions, I just treat them individually and I use the same technique. So let's go through a few examples and we can sort of see the technique for differentiating and finding the gradient function. So y is equal to x squared plus 2x. Okay, so we're going to do dy dx. Now, the principle is you take the power, so 2 goes out the front, and then the power is reduced by 1. The next term, I take the power, which is 1, I multiply it out the front, so that's not going to change. So it's going to be 1 times 2x to the power of 0. And so this just becomes 2x plus 2. And that's the derivative. This is the gradient function of y equals x squared plus 2x. Gives us the gradient of the curve at that particular point. Okay, let's do a next one. Let's do f of x. F of x is equal to 2x cubed plus 4. Alright, now we want to find f dash x. Now what happens? Well, I've got this 2 in the way, but that actually just will stay there. The 2 doesn't affect, or constants multiplied by a function don't affect the differentiation process. I'll just kind of write that down in a second. So the power of 3 comes down. 3 times 2x, and then the power of 3 we reduce by 1 to 2. Plus, now we saw that any constant is going to be, derivative of a constant is 0, so it's just going to be plus 0. And it's just a matter of saying 3 times 2 is 6, so this becomes 6x squared. Now again, to just emphasize what this means, if you have this function 2x cubed plus 4, anywhere along the curve, if I take the x value and substitute it into 6x squared, that's its gradient function. I can find the gradient of the curve at that point. Or, another way to say it is the instantaneous rate of change. Alright? Okay, let's try this one. Find derivative of x to the power of 4 minus 3x squared plus 5x. Okay, now in this case we don't have y equals or f of x equals, but that's okay. If I want to say differentiate with respect to x, I can just write it like this, d dx. So you know, if I had y equals, I would put y there, but this is just a derivative of x to the power of 4 minus 3x squared plus 5x. And that's equal to, well, if we have a look, the power of 4 comes down the front, and then it's now x to the power of 1 reduced, so 4 minus 1, which is 3, minus, here we've got x squared, so it's going to be 2 times, remembering that the constant is unchanged, x to the power of 1, plus, well, the 1 from the power comes down, it's going to be 1 times 5x to the power of 0. Now if I sort of simplify this, 4x cubed minus 6x plus 5 is the derivative. So let me just make a note about the constant. Note. If has a constant in front, it will also be multiplied by the derivative. What I mean is what we kind of did in the example. So if I have a constant k, So if I have k times f of x, when we differentiate, it becomes k times f dash x. That's it. So the k is always going to be there. It's just that in the differentiation process, like up here, I took the 2 down from the power of x, and now it's 2 times 3, but that's kind of like my k. There's a 3x squared. So I just differentiate x squared, and then make sure I multiply it by 3. Now, we are going to have a go at some exercises. So let's have a go at exercise 8.3. Now 8.2 we skipped for very purposeful reason. Exercise 8.3, and I really want to emphasize that when we find the derivative, it's the gradient function. It tells us the rate of change, the instantaneous rate of change at any point of x on that curve. Okay, have a go.